Thank you for the introduction. Well, I want to start with me feeling like an alien today because I'm in this group of experts for facades, and what I'm going to present to you is not essentially facade systems. It's not very fancy and beautiful pictures of tons and tons of facades. However, I hope that still you find what I will introduce to you interesting. So, the topic is the implementation of an adaptive high-rise building. And yeah, well, this is the thing we are currently doing in my institute. I'm from the Institute of Lightweight Structures and Conceptual Design. The professor is Professor Werner Sobek. I don't know to whom of you he's a name, but well, if not, then come to me, I'll explain it to you. Pardon? Dubai Opera, for example, yeah. However, my institute has a long history of very famous heads of the institute. So we started with Jörg Schleich, and we also had Frei Otto as an architect as head of the institute. And when Werner Sobek took over, then the research kind of shifted. And right now, we are focusing on adaptivity, because we think this is the solution of the most pressing and urgent problems of today. And I will introduce to you those problems we're working on to give you an overview. Well, this graph here, probably you've seen it, well, I've seen it today quite often, actually. I was surprised how often I saw it. And this shows the population development from 1950 up till 2050. And we are expecting a huge growth, and the increase will continue until 2050. So we will end up with 9.7 billion people by that time, which means that a net sum of 2.2 billion people has to be added to today's population. And if we think back, when was the world last 2.2 billion people large, then it's 1930. And if you consider how far the industrial countries were developed by that time already, how much we had, how much infrastructure we had, and if you think that all of that infrastructure, Paris and London from 1930 and Berlin and the Suez Canal, if all of that has to be rebuilt until 2050, then this is a huge step to do in just 32 years. And most people will be added to third world countries and second world countries, so the less and the least developed countries. The first world only gets like a small bit, 35 million more people, and the second world, 1.4 billion people until 2050, and the third world almost doubles by almost 1 billion people. So this is the urgent, or this is where it matters. I can't show it, sorry. And this will be the futures of our projects. And where will all of that happen, all of that change? Of course, in the cities, because if you also calculate the percentage of the urban population, it's rising up to 2/3 of the whole global population that will be living in cities by 2050, which is also 2.2 billion people more in 32 years. And if you look at some of our cities, they're already bursting, and they're not capable of getting more people into them. So there will be new cities developing, and just increase of city and increase of density. And here also, the less and least developed countries are having a really big increase here. On the map, it looks like this. This is 1970. You see there are just some red dots that mean 2 million or more people living in one city. They're concentrated, one in the US and in Japan. Right now, this looks totally different. Much more blue dots are appearing, but also many more of those red dots that are the big mega cities. And if we look ahead to 2030 this time, this is also a big step to take. So we have so many more of those mega cities coming, and those mega cities that need space and also need infrastructure and also need resources. And I try to calculate. So if we just take the amount of living space that we would have to apply, or that we would have to give those new people on Earth, then we end up with 5.7 million hectares of additional living space. And this is just for your flat. So it doesn't include the infrastructure you need to get to your flat. It doesn't include the infrastructure you need to your working place. It doesn't even include the working place. It doesn't include the educational or the religious places. So this is just living space. And then you have to add around 11 million hectares as an increase of living standards, because right now we have the industrial countries and we have the less and the least developed countries. And all of those less developed countries are urging for the next step. And who would we be to blame them, and who would we be to say no to them? So they have the right to increase their stadium of development. And this will automatically have, as a result, the increase of living space. So if you take 40 square meters per person for industrial countries, 20 square meters per person for less developed countries, and 10 square meters per person for least developed countries, you end up with around 11 million hectares. And also you have to take into account that by 2050, due to the increase of the oceans and the desertification, there will be a lot of climate refuges that will also need to have additional living space. And this is the big number you'll end up. And if you multiply that by 2.2 tons, which is around about the medium you could have for a single family house, then that huge number, 368 million, this should be million tons, is what you get, or what you have to have until 2050. And there's a researcher called Krausmann, he's also Austrian. He just tried to calculate how much the material stock on Earth right now is, so how much is in our built environment, and it's 800 gigatons right now. And what happens if we keep doing it as we are right now? Then we see the blue line, it will almost double until 2050. And if we keep on going, if we give all of those less and least developed countries the same status as we have, it's the standard 2010, then you see how exponentially this increases. And what would be the answer for urban planning? So I have architecture as a background, and this is what's interesting most for me. How are we reacting? How are the urban planners of tomorrow and today reacting to this crisis? Is it more or less a horizontal spread out like Mexico City is? Would we have more or less low and mid-rise houses? And would this be the consequence we would want or we would need? Because if you have a horizontal layout, then of course you need to get from A to B, and if B is so far away from A, then you'll take the car, and well, this is what you get with the smog then. Or would it be maybe going down into Earth as an earth scraper? This also exists mainly in the mind of architects, but it could be a solution. I mean, we do have a lot of space down there, so why not try? But I don't know about you, but I see a few conflicts here. And so this would be another option, go out to the oceans. This is also quite intensely looked after by architects. But I also think that we're stuck with our ecosystem, and we're already destroying the ecosystem Earth, so why also occupy the oceans? And probably all of you think this would be the logical consequence and the logical answer. And I agree. I do think that vertical expansion would be one possible solution. But we as researchers, we are not looking at it and saying, yeah, that's it, let's just do that. But we try to find out if it's really the solution and if we do have all of it in contemplation. So stacking the features of a city on top of each other and to have everything quite close and quite dense does sound reasonable. If only there wasn't the problem with the wind. horizontal forces that are forcing our building structure to be more compact and to be heavier than it's actually needed. I'm sure that all of you are familiar with this graph. It's from Fessler-Kahn, and it's already decades old, but still quite up to date, I think. So if we were only stacking one story above the other one, then of course also the structure would have to be heavier because, I mean, you have all of the story weight above of each other. But this would only end up with a linear graph, and it would end in the blue, with a blue line. But unfortunately, we are not able to build our high-rise underneath a big dome. So the horizontal forces by the wind are forcing us to include much more structure, so to make our structure heavier and more compact. And then we end up with a purple line. And this is quite a big gap. And with what I'm going to introduce to you now is our try to close this gap a little bit more. So since last year, we have a collaborative research center. It's funded by the German Research Foundation. It's called Adaptive Skins and Structures for the Built Environment of Tomorrow. And as you can see with the name, we are trying to find adaptivity, or to include adaptivity into skins, so facades, and also into the structure. So this is at least something that has to do with facades. We will include different kinds of facades. For example, as you can see here in this small sketch, we would have, for example, liquid crystal-based facades. So it shows a facade which is composed of hundreds and hundreds of small pixels, and every one of those pixels can be darkened by an algorithm or a computer program. So if you're in the room and it's winter, and in winter in Germany it gets quite cold, so you'd want the sun rays to come in. However, you're not able to work because the screen is only reflecting the sun. So you need something that prevents the sun from blending you. And with this facade, you're able to just darken that one dot that is blending you. And you can have it as an algorithm so that it will follow the sun throughout the whole day. And by that means, we can get the sun rays in, but still have the blend factor out. Excuse me. So, what we're trying to do here is to include adaptivity into the building structure and into the facade here. And in terms of the facade, in order to have a better well-being for the occupant and for the user of the room. And we'll also have different kinds of facades. So there will be textile facades that are very thin layered and very light, in order to save material, of course, and in order to save also weight. And so the outcome of our building is still open because the researchers for the facades have only just begun. So maybe if I come back in 5 years, I can actually show you a lot of different facade types in this session. And the other part is, with the adaptive structure, it's something that we call ultra-lightweight structures. So ultra-lightweight means it's one step further to lightweight structures. Lightweight structures have come to an end at some point because if you make them thinner and lighter and thinner and lighter, then you somehow end up with a design that the design is not the dead weight anymore, but that it's, for example, the snow. So if the snow gets heavier than your dead load, then what shall you do? And this is why we include active elements, in this case hydraulic actuators, into the support of this shell. So the shell is spanning 15 meters and it's only 4 centimeters thin. And this is only possible because we have 3 active supports. And we have a lot of sensors that are included into the structure that can simultaneously give signals to the actuators and tell them, oh, here's wind or there's snow, please react. And the solution to it is that you will have the structure and you have a discentered load on it, and the actuator pushes the structure back into the regular shape so that you have a complete neutral position again, and you avoid the additional forces on the structure. And thereby you can save resources because you can make it thinner. So this was theory, and this is a graph that shows the problem between, sorry, it's German, but I will translate. It's the active design here and passive design on the right-hand side. And the thing is that you have, with the passive design, you have a lot of dead weight load. So the embodied energy is quite high, but in the end you will have maybe less operative energy. So that's why the graph goes down in the end. And with the active design, it's actually the other way around. You will have less embodied energy, but you will have more operative energy. And so with the adaptive design, you will find the optimum in the middle between, well, not too much operative energy, but a lot of embodied energy saved. So our goal is always to save resources, because the sun gives us much more energy than we could ever use, but we do not have unlimited amount of resources. So there are two ways that we were looking at for the actuation of a building structure. And you can either actuate parallel or serial. So parallel means that the actuator is only partially in the load path, which has the big advantage that it's consuming less energy, and it's also only dynamic loads are on the active structure, because the rest is covered by the passive structure. With a serial, of course, that would be much more neat to have a serial actuation. It's consuming less resources because you don't have two columns. But, however, the critical safety aspect is quite important, and that's why what kept us from following this to the end. So they're either, depending on the location of the actuators, you can either, if you put them in the columns, like it's shown in the left-hand side picture, then the advantage is you can spread out the forces from that bit that is highly under forces until to the others, and so you can spread out the load and have a different load path. And and if you put the actuators into the diagonals, then you make the system more rigid for a small period of time, and you prevent the rhomboid shape. So we will place 16 actuators into the diagonals and 8 into the columns. And the thing about this whole project is that it's super interdisciplinary. So I'm not only working with civil engineers, I'm also working with system dynamics, I'm working with mechanical engineers, and we're all trying to solve this problem. And the tricky part about it is that it's still a building, but it sometimes looks like machinery, which I, as an architect, do not like that much. But so we're always trying to trying to discuss it out and see how everyone gets their will. And this is the effect that we want to have. So if the wind is putting horizontal forces onto the building, then without our actuators, we would have the black response. And you see how big the difference is compared to the blue one, because we can somehow dampen it without having a big, heavy damper on our top floor. But we can regulate the rotation, or the the swinging of the high rise, and all just by the actuators. And this is where it's going to be. It's going to be on our campus at the University of Stuttgart. the famous tent by Frei Otto is to right-hand side, and we will have two towers, because one tower, the left one, will be the actual demonstration tower, and the other one will be a staircase tower with all the support elements and all the shafts in it, so that our demonstration tower will be really clean and by itself. It will be quite extraordinary compared to the rest. We do count as a high-rise. I know for these standards here, we probably are rather a low-rise building, but it's 12 stories high and 37 meters tall. And this already in Germany counts as a high-rise building. And we have a slenderness ratio of 1:7. That's why we have a quite small ground floor area of just 5 by 5 meters. And the facade will be a thin membrane layer at the first step, because we are waiting for other companies to test some modules, some facade modules here, and we're also waiting for our research outcomes during the next years. And yeah, so this is how it's going to look like. It will be more or less like a platform for different systems and different facades. And I'm speaking out to you as facade producers. If you have a facade you want to be tested and you don't know where to put it, this might be it. So please don't hesitate to question me about this, because we do have some free stories. And as I said, we're waiting for our results, which is going to take a while, because research does take a while. But yeah, so our facade is 5 by 3 meters. That's one element. And we will offer everything you might think of. So we'll have sensors there that measure the humidity, that measure the translucence and the transmittance and the U value, everything you could think of. So it's actually a really good platform to provide some tests. And we hope to answer the question that I asked before. So we will also know how much our building weighs. This is one question I find hard to be answered by other architects and engineers. We will also have an answer to, does it work to have actuators and to replace resources or material by energy? And yeah, maybe if I come back next year, then, or I'm sure, because it's going to be built in the next month, so if I come back next year, I can show you some actual pictures, but for now this has to do. And with that, I would like to finish. Oh yeah, this is how it might look like, just a draft. Okay, thank you so much.
Thank you.